you have a lot of IO tasks that are happening, and those IO tasks would be running in an interleaved manner. All of those tasks are supposed to be independent. If they are not independent, we cannot run them concurrently. So we have essentially a single thread of execution where all the tasks are run one by one, and they are suspended and resumed periodically by the event loop, as we learned in the reactor pattern. So benefits of async IO is you don't need more resources, and the program is quite simple. Then your IO task won't block. Even if it is blocked, the whole application doesn't stall at all. So things are progressing all the time. So food for thought for all of you. With async IO, can we solve one of the perennial problem in Python called GIL? Just keep thinking about it. So let's understand how async IO programming is available in Python. So Python has web framework as well as programming module for applications. So we will start discussion with async IO module. So async IO is part of standard Python distribution now. It has been released latest in, I think, early this year. And applications are backward incompatible with async IO because it's available only for Python 3.4 onwards. So async IO is a completely new way to write your Python applications. You need to think things from scratch. You need to learn what are the constructs available in async IO module and how to write your application using those constructs. So async IO is essentially the same as we learned in the async paradigm. It gives you a single thread of execution. That thread would be handling multiple events. Each event is actually a task. So to run those tasks, it uses cooperative scheduling. So it's a fancy term for just suspending something in progress. So if you find that a task is stalling the application, it will suspend itself, and when the event is done, it will be again resumed. So in the meanwhile, we can run another task. So the calls like select, epoll, all these calls are wrapped in a library called libevent. So this library is common for Windows and Linux, and the underlying implementation is different for both the operating systems. So async IO internals, so these are the major components of async IO module. We will understand them one by one. So let's start with event loop. So as we know that it's a single thread. So this thread would be responsible for running your application. So the major responsibilities of event loop in async IO is to schedule a task. You can register callbacks. It can handle signals. It can allow creation of transport and connections, as well as it provides an interface to thread pool in case you know that a task is going to take a lot of time, so you don't want to run that task in your event loop. You can offload that task to a thread pool. Next is a coroutine. So we all know a normal function in Python. So a function is just a bunch of lines of code that runs serially one by one. Coroutines are special functions wherein you can suspend execution of your function at will and resume it as soon as the particular event is done. So say in the beginning we had an example wherein we are reading a data from a socket, and if that call takes a lot of time, in that case we can suspend the execution, allow some other task to run, and when the data is available, we can resume the execution of our function. So coroutines are decorated by asyncIO.coroutine. That's a keyword. And in async IO, coroutines would essentially have a yield from statement. So we'll learn about it in an example. So third important construct is a task. So coroutines are run by a task. They are wrapped in a task and then put in the event loop. Event loop will schedule the task, and if a coroutine suspends, so task will allow another task to run, and as soon as the coroutine resumes, it will pull the task in the event loop. So actually in async IO, the event loop employs two queues. So these queues correspond to two different category of tasks. So at any point of time of your application, while it's executing, you have tasks that are either ready to run or that are blocked on some event. So tasks that can be run immediately are kept in the ready queue, and if we find that a task is about to block, then it will be moved to a suspended task queue. If you want to create a task in async IO, you just have to call either the async function, or you can call a create task function. It has been added recently in Python 3.4. Now, since IO is essentially an operation for which the result is available in future, so futures are unresolved references wherein we don't know when the result will be available. It could be a value, it could be an exception, anything. So here we have an example. So we create an event loop with get event loop call, and we create a future object. Async IO.async will here you can see. So async IO.async. So async IO.async will create a task. That task is actually running a coroutine called slow operation, and we have a yield from statement here. So as soon as the future object is called as an argument to the coroutine, and we see that future.add done. So as soon as the future is available, we'll call a callback called got result. Now let's go to the coroutine slow operation. Here, as soon as the execution of the coroutine starts, we sleep. There are more constructs called transport and protocols. So the majority of your work will be done in these constructs. So transports are a way to connect. So you have sockets, you have pipes, you have SSL connections, and protocols are just applications. So async IO gives you wrappers which are non-blocking for various type of calls, like socket creation, reading, writing from the socket. Let's understand async IO in detail with the execution of the statement in the beginning of the coroutine suspended. So while it is suspended, another task can begin, and it will start its execution. So whenever the connection is created, the coroutine is resumed, and it will move to the next statement. The best way to understand yield from is to just ignore them. So that's what Guido has told. So you don't have to look at them, just ignore them and just believe that it is running synchronously one by one.
So one more thing to add here is, like, even though these two tasks are synchronous, but we need the operations that are under my subscriber. Those are synchronous, because the first one should complete only, then the second would make more sense. But in itself, these operations are again async. So that is one important thing to note here in this case. Yeah.
So we have one more example. So we create an event loop. So event loop is a must for any async IO application. So in this loop, we create 3 tasks, which is a combination of IO and CPU tasks. So all 3 tasks would be running concurrently. So good thing with async IO is you don't need a very hi-fi machine to run your application. Even with a single core and without more memory, you can run your application efficiently. So as soon as all the tasks are done, we will wait till all of them are complete, and as they are complete, we'll close the loop. So this is an interaction with async IO module in Python. Now I would hand over to Chetan to help us understand the web framework, which is async, and it's called Tornado. So Chetan.
Thanks, Vishal. So all the concepts that we learned till now, like in async paradigms or with async IO, all the same are at the heart of any asynchronous library. So if you learn about the basics, you can implement it anywhere. That's the philosophy that we have. So a similar thing can be done for Tornado as well. So the event loop that we started with is implemented in Tornado with IO loop class. The coroutines are implemented with the gen.coroutine classes, and future is implemented with the event loop starts, right? It will come up and first see that there is some async call happening. So it will just handle it to the event, give it to the event handler or the callback called handle_request, and prints the before event loop starts. So the output here would be interesting to understand. So it prints before event loop starts. That's because the IO task is made asynchronous, and only when the result is available will the callback take the event and go ahead and print the success and the response body or error, whatever the case may be. So again, how are core routines implemented in Tornado? So in async IO we use the decorator at asyncio.coroutine. Similar decorator we have in Tornado, which is tornado.gen.coroutine. And one thing to note here would be is instead of yield from, we are using yield keyword. So so this is the yield. So in async IO we had yield from. So that returns a generator. Here in this case it results of one of the values of the generator. So and response variable here is a future. So only when the google.com response from google.com is available will that value be filled in the response variable. So it's again similar to what we have in async IO. And as Vishal also gave an example of creating our own task, in Tornado also we can create our own task. Again the same paradigm. It's just that we wrap it under another decorator gen.engine, and we create a synchronous task with gen.task. So we can also create our own future. Slightly philosophical, how can create our future, but yeah. So the server side code is similar to what we had seen 2 slides behind. So we again take a async HTTP object and then make a fetch call to google.com. But in this case, async HTTP class is written by our own, in our own language, which is myfuture.py, and we wrap it around decorator return_future. So it prints essentially in my fetch and then returns you a callback. So callback here is nothing but a function test, which will print in test and the argument. So argument here would be the date timestamp that gets printed. So it's nothing difficult to understand here. It's the same philosophy. It's just that in async IO you do it in a slightly different way, or a syntax is different. In Tornado you do it in a different way, but the underlying philosophy is same. That's what is the most important thing for us to understand here. So we did some performance tests as well. So it is no coroutine or anything here. It's a simple program. So the blocking class takes a HTTP request, which is a synchronous library call, and makes a call to /work URL, and async makes a async HTTP object and makes a call to /work. But what is /work? /work is nothing but a construct that is added to IO loop, and it waits for 0.5 seconds. So here are some of the results that we got through the Apache bench test mark. So we found out that async paradigm helps you relate to more requests per second, and the time taken per request is also lower. So those are some of the results that we got. So let's conclude this session with the learnings that we have. So we both believe, Vishal and I, we believe that async programming is easy to understand. Maybe the mindset that we have to build is slightly different. It's not similar to the conventional programming approach. Python has a new module async IO, which is quite extensive, can be easily utilized, and if you use async, you get good performance improvements. Responsive web applications can be built easily. the recommendations that we have is, of course, async is not a har marz ki ek dawa kind of approach. So it's not a holistic solution to all problems. You need to understand and use these philosophies. And you can also look at other paradigms such as multi-threading or eventlets, or there are some new languages that have come up like Go and Scala that provide for concurrency modules. So yeah, with this would like to conclude the talk. There's some references that we used for the talk, and you can contact us here. Thanks. Okay, so let's have some discussion if you guys have.
You've spoken about a couple of frameworks, that's Tornado and Twisted. Now I've used Twisted extensively, but I don't know what the difference between Tornado and Twisted.
So that's the whole, yeah, so just to repeat the question, what's the difference between Tornado and Twisted in an async context? So as we understand that we haven't used Twisted extensively, we have used Tornado, and somebody would have used Twisted extensively. But our philosophy of this talk is, if you understand the basics, like what are the different paradigms that we are working on, it's not difficult for us to learn the other one as well. Yeah, so yeah, so async programming, as we said, requires a different programming mindset. So that happens, it's true for Node.js as well, it's true for Python as well. So if you go callback, callback, that way you get complicated in your own thing. But the thinking should be clear and design should be clear. I think these problems are best solved in the design mode itself. Else you end up using promises in Node.js and all. Right.
And secondly, for really processor-intensive tasks that you want to run, they all run in the reactors event loop, which is in the single thread. So you have another construct that says call from thread, and when you return the thread, when you read that thread back, you can, like, you use it in some way, you can have a different VM underneath. How good is that? Those people are very key concerns to build a really large asynchronous app. So how is that in
So to repeat the question, we have two concerns here: chaining of coroutines, as I understand.
Chaining of callbacks.
Okay, and then the second question was call from thread related to CPU operations. So async IO programming does provide certain chaining of callbacks, as you can say. So the example that we had published with the subscriber thing. So as I told, like, even though the task may be asynchronous, all these three operations are performed in synchronous way, but individually these operations are asynchronous. So we can go ahead and create, go inside and create chain of callbacks as well. So that is available. And relation to CPU, how is CPU handled in the event loop? Call from thread.
I didn't get the question.
I think.
What was your question? Could you? Okay.
Then is there a construct that enables me to yield into a different thread and then yield back into my thread?
You can use a thread pool for that.
But again, thread pool, right?
Yield ka problem.
See, when you are running a CPU task, why would you want to yield? Why would you want to yield? I mean, the async IO is primarily the use case. Yes, it's only for IO-driven application.
Sometimes you might have a task that would be CPU intensive and you want to intermix it, right? So
You can.
you want to execute that on a different core or a different bit block on the CPU.
Okay.
Processing
See,
Do that with Twisted. I mean, it's not a very neat way of doing it, but you can do that in Twisted on Python 27.
okay.
I want to know if that's possible with async IO.
We are not aware of it then. No.
Yeah, multi-processing.
I think threads you can switch. That is not possible in async IO.
मैं बोल रहा async task जो है वो तुम्हारा threaded होना चाहिए तभी वो कर सकते हैं. Okay.
Any other question? Oh yeah, please. I.
Couple of libraries are available to connect the database.
Okay.
So these libraries are blocking IO port.
Okay.
Connecting to Oracle server or other servers like SQL server. So what is the provision to do for less than Python version less than 3.0? So is there anything we have so that we can avoid the dropping one?
Yes, for earlier Python versions, you can either use async core. So there is another module. So actually, async IO is a refinement of older modules like Twisted, Eventlets, async core, async check. So if you want to do async operations for old Python versions, you can try any of them. Did I answer your question? Or
Also, let's say your question of database, right? So let's say if the framework like Tornado, we have certain async libraries for database operation. So that can be leveraged. So in this case, if you want to interact with MongoDB and Tornado, so MongoDB has a module called as Motor. So Motor can be integrated with Tornado and then you make everything async. So that's another solution that is available. So you need not go to async IO for that, or you need not go to Python 3 for that. You can still do all these things in Python 2.7. Okay, thank you. Thanks a lot, guys.
thank you very much for your time.